So hello everyone, today we will be starting week 9, that is heat transfer in bioprocess systems, and the last lecture will be based on scale up. So we can quickly recall the last module. So initially we discussed mass transfer theory, particularly the Fick's law of diffusion and two film theory. Then we discussed the role of this mass transfer, particularly in the aeration and agitation. Then we discuss aeration separately and agitation separately. In the aeration we discuss as the mass transfer resistance lies in the liquid film, then how to calculate this film mass transfer coefficient KLA using experimental method and also different correlations, and followed by that we discuss agitation mixing, what are the different components of mixing including impeller, baffle and propellers, and then we discuss power requirement with gas system and ungas systems. Now today we will be discussing the first topic, that is heat transfer in bioprocessing. So in this lecture we will be mostly covering on mechanism of heat transfer. So there are three mechanisms, we will briefly discuss each one of them: conduction, convection and radiation, and followed by that we will be discussing a few heat transfer correlations to estimate the heat transfer coefficient. So mechanism of heat transfer: the heat exchange occurs between fluids and many times there will be no physical contacts. So it means there will be some intermediates between that. For example, if you consider the heat exchanger, so there will be metal between the two hot fluid as well as in cold fluid. So for example, it says transfer of heat through metal wall that separate two fluid streams, hot and cold streams. So one option is there should be sufficient surface area that is necessary for the efficient heat transfer rate, and if it is a straight tank bioreactor, then there should be a sufficient turbulence that can be generated through agitation. Now if you remember, there are three mechanisms of heat transfer, that is conduction, convection and radiation. However, in the bioprocess we will be seeing that conduction and convection mostly dominate. Conduction, we will quickly be revisiting these concepts, may be known to most of you, but we will be quickly revisiting these concepts. Conduction, this is also known as molecular heat flow. It means transfer of vibrational energy between molecules or movement of free electron. So here this conduction happens in the same material, and this is important particularly in metals and occurs without observable movement of matter, because it is happening through the energy transfer between molecules or movement of free electrons. So there is no different phase here, it is between only one material where conduction is taking place by the flow of electron. So here one important parameter we will be seeing, the material should be conductive, that we will be discussing in subsequent slides. Next is convection. This is very much important, and as the name suggests, it requires the movement of macroscopic scale, and particularly it is confined to the gas and liquid. Now there are two types of convection. One is natural convection. So in this case temperature gradient in the system generate localized density difference that results in flow current. And forced convection, we are going to have this flow currents are equipped with external agents like stirrer or pump and are independent of density gradient. And as we are using the external sources, it achieves higher rate of heat transfer. So, natural convection, the flow is due to difference in density and that originate because of temperature gradient. And in the case of forced convection, we are using external agents like stirrer or pump to induce the flow. So, convection, it is between two different fluid streams, and in between there will be one metal wall or one this separating boundary will be there. Third one is the radiation. It is known as electromagnetic transfer. So, here the emission or absorption of electromagnetic waves occurs and energy radiation happens in the form of wave, and radiation absorbed by the matter appears as heat. So, radiation, as we know, this is coming in the form of wave. So, it is important at much higher temperatures, and rate of heat transfer is given by Stefan Boltzmann law that says Q is proportional to T to the power 4, and the proportionality constant is Stefan Boltzmann constant, area and surface emissivity into, you can say, T1 to the power 4 minus T2 to the power 4. Particularly if you remember in bioprocessing, the temperature is mostly less than 100 degrees centigrade. So, radiative transfer is negligible as compared to conduction and convection. So, in this lecture we will be mostly focusing on conduction and convection. Radiation part will not be discussed here. Now, conduction, as we have discussed briefly, the heat transfer occurs through fluid separated by a solid wall, and rate of heat conduction through the wall is given by Fourier's law. It says rate of heat transfer is proportional to the temperature gradient dt upon dy, and the proportionality constant is thermal conductivity K. K is thermal conductivity of the wall or the metal, into A is the surface area perpendicular to the direction of heat flow into temperature gradient dt upon dy. Y is the distance, and what will be the limit of y? Limit of y will be B, that is the thickness of the wall. Now, heat flow in positive can be in positive direction and in the negative y direction. It depends what is the value of T1 and T2. So, it can take place, let us say, from T1, T2. If T1 is higher, it will take place in this direction, and if T2 is higher, if T2 is greater than T1, then it will take place in this direction or this direction. So, if T1 is higher, it is called negative gradient. If T2 is higher, it is called positive gradient. But overall, there should be difference in temperature for heat transfer to take place. So, heat flux, many times if area is not there, we directly calculate the heat flux. The Q is defined as capital Q upon A. So, now this becomes minus K into dt upon dy. Now, the unit of heat transfer rate is, we write in the watt, and imperial unit is BTU per hour, and this is the conversion factor. 1 watt equals 3.412 BTU per hour, and if you write in terms of heat transfer per unit area, it becomes watt per meter square, and here in imperial unit is BTU per feet square per hour, and the conversion factor will be 0.317. So, as one important parameter in the conduction is the value of K, as the heat transfer is directly proportional to the value of K. That is very important. So, if you just see for the metals, its value lies in the range of 50 to 400 watt per meter per degree Kelvin, and if you see for the plastic and insulator, it lies in the range of 0.2 to 0.5. So, what it suggests, if you want to have a insulate a pipe to avoid the loss of heat transfer, then we can use insulator which have less value of K, and if you want to have a good heat transfer, then we should choose the material which have a higher value of thermal conductivity. Now, if we will consider steady state conduction, so it says there is no accumulation or depletion of heat within the wall. It means the rate of heat flow must be same at the each point of the wall. So, if you write this Q as minus K A dt upon dy, and if you consider steady state, it becomes Q into dy minus K A dt. So, we will simply end up Q into y minus K A, this will be T plus constant, integration constant. Now, we can use both the boundary condition at y is equal to 0, t is equal to T1. So, we will get the value of constant. So, we will get the value of constant as K A T1. So, it becomes now Q, you apply this boundary condition, you will get the constant as, because y is equal to 0, this term will be 0 and this becomes K A T1. And if you put this value, so we simply get delta T. So, it says Q to y equals minus K A T 1 minus T, because you can remove this minus sign, or you can say K A delta T from one side. Now, if you integrate, what will be the value of y? It will go from, in fact, here itself you can write, if you are integrating from 0 to b, so this y can be replaced by b, q into b. So, it becomes q equals K A upon b delta T. Now, this is driving force, and this term is resistance. So, we can simplify in other words like Q as delta T driving force upon Rw as a resistance, and Rw is B upon Ka. Okay. So, what it says, wall thickness is directly proportional to Rw and surface area is inversely proportional to Rw. In addition to these thickness and area, there are other factors that is called nature of material that also affect the heat transfer resistance. So far we have discussed here the steady state conduction, but many times, particularly during startup and shutdown, there is a transient heat transfer. In that case, we need to consider unsteady state conduction, but that topic we will be not discussing in this lecture. Now, many times there may be more than one material, let us say 1, 2 and 3, they are in the series. So, we need to calculate the total resistance. So, it simply becomes R total as summation of Bi upon Ki into A. So, we can calculate total resistance. Now, we need to also calculate total delta T. So, delta T will be delta T1 plus delta T2 plus delta T3. So, in this way now we can write the same, this Q as delta T upon R total. Now, if I write here what will be the R total here, then R total will be, let us say for 1 B1 upon K1A plus B2 upon K2A plus B3 upon K3A. So, this can also be simply written in terms of R1, R2 and R3. Now, next comes if the heat transfer. So far we have discussed heat transfer through the metal or through a material. Now, heat transfer between the fluids. There, let us say one side there is a cold fluid and other side there is a hot fluid. So, here this heat transfer is taking place through conduction, but heat transfer by the fluid motion will take place through convection. The convective heat transfer in agitated vessel, this is rapid and happens due to mixing and turbulence. So, one is the agitated vessel where this heat transfer is taking place. Other option is there is a heat exchange equipment. There also the heat transfer is taking place, and between the two different fluids streams, between the two different fluid streams, hot and cold, the heat transfer takes place. But once you are having this additional metal wall, it offers additional resistance to heat transfer, and from where this resistance comes, it comes in the form of thin thermal boundary layer near solid surface, and that controls the rate of heat transfer. That we will be discussing in the next slide. What is this thermal boundary layer? Now, heat transfer at pipe wall. The heat exchange happens between hot and cold fluid separated by a pipe wall, and what we are assuming, the both fluid are assumed to be turbulent on either side of the pipe wall. So, if the temperature of hot fluid is Th and the temperature of cold fluid is Tc, so at the wall we will be writing the temperature at the wall is Thw and temperature at wall is Tcw. Now, as we know, once there is a surface which is coming in the contact of liquid, particularly there will be formation of boundary layer form due to viscous drag when fluids contact with the solid, and because of this boundary layer, fluid near the wall moves slower, forming a thin sublayer or the film. So, because of this stagnation, the turbulent core exists away from the wall, and most mixing and heat transfer occurs here. So, there is a, you can see clearly this is the wall, let us say this is the wall and this is a fluid. there will be formation of boundary layer formation. And now as there is a boundary layer, so it is expected there will be thermal boundary layer as well. So this is critical for the heat transfer, and it shows resistance to heat flow due to slower flow, and heat transfer occurs mainly by convection. The temperature drop from the bulk fluid to the wall happens this layer. So from TH to THW and from TCW to TC, it happens in the thermal boundary layer, and usually it is thinner than the hydrodynamic boundary layer. So you just see this is a hot TH and this is the stagnant liquid film. When it is crossing through it, it is reaching to THW, and from THW to TCW the conduction is taking place through the metal wall thickness. Conduction is taking place, then again from TCW it is reaching to TC. So, and these two are the, from both the sides you can see the liquid film, that is the boundary layer. Now first we will be considering individual heat transfer coefficient. Resistance encountered in the heat exchange between the fluid. So there is, we have already seen hot fluid film resistance at the wall, resistance due to wall itself, and cold fluid film resistance. So we are seeing three resistance. You can start with 1 here, 2 here and 3 here. So for steady state convection, the rate of heat transfer for each layer fluid is proportional to delta T, temperature difference. This is the, and proportionality constant is H, heat transfer coefficient, into area into delta T. So this is the equation for convection. So H is the individual heat transfer coefficient, A is the area of heat transfer, and delta T is the temperature. Now there will be two delta T. One delta T will be TH minus THW, other delta T will be TCW minus TC. So there will be delta T for hot fluid film and delta T for cold fluid film. So in this equation there is no thickness term here like in the case of conduction. So instead of thickness, the H, heat transfer coefficient, is used, which is similar to the thermal conductivity in the conduction heat transfer. So once this, as we know, there is a stagnant film, or you can say the liquid film near the solid. So this value will be affected by the system geometry, flow condition, as well as the fluid property. So rate of heat transfer in the each fluid boundary layer is depending on the temperature difference as a driving force and resistance. The similar to the conduction, we can write Q is H A delta T, and it can be written as delta T upon H A, and so 1 upon H A is the resistance and delta T is the driving force. Now we are going to have two resistance, one is the HH or hot fluid, and one will be RC, will be 1 upon HC into A. Now we can combine all three resistances. Hot film metal and cold film. So, in that case we write U as overall heat transfer coefficient U. And what are three resistances? One is coming from the RH, other is coming from the RC, and in between RC and in between there will be RW. So, this is the conduction, sorry, this is convection, and this is conduction. Now, depending on the value, let us say for low value of U, the system can transfer limited amount of heat, and the value of U can be increased by adjusting different variables like fluid velocity, stirrer speed, and heat transfer area must be relatively large, as heat transfer is directly proportional to area. But if you increase the area, it also causes increase in the cost of equipment. So, this is the equation of convection, and what we are going to replace? We are going to replace H as U. And what are the three resistance? We have already discussed. So, three resistance is RH, RW and RC. So, if I write Q as U A delta T, so you can written delta T upon U into A. So, total resistance is 1 upon U A. So, it says RT is RH plus RW plus RC. So, RT equals RH RW plus RC. The RT is 1 upon UA, RH is 1 upon HH into A, RW is, it is from convection, B upon thermal conductivity into area, B is the thickness, plus 1 upon HC into A. And here if you consider there is no significant difference in the area, so we can consider the area. So, it becomes 1 upon U as 1 upon HH plus B upon K plus 1 upon HC. So, in this way one can calculate the overall heat transfer coefficient. Now, in addition, as the solid surface is coming into contact of fluid, there may be fouling, which is called the deposition of dirt or scale, and this offers additional resistance to heat flow, and ultimately it reduces the overall heat transfer coefficient, because resistances will be increasing. Now, earlier we considered the three resistances, now we are going to consider the 5 resistances. First is hot fluid, thermal boundary layer, then fouling layer, then pipe wall, again a fouling layer, and then cold fluid. So, if we just see the figure here, so this is the liquid film, and now we are adding this. So, this is resistance 1, resistance 2, fouling layer, 3 pipe wall, 4 again fouling layer, and 5 is the stagnant film or thermal boundary layer. So, now there will be 5 resistances here. So, these 3 we have already discussed. So, fourth one is 1 upon fouling layer of hot fluid side, and this is the fouling layer at cold fluid side. So, now there will be 5 resistances, and so it decreases the overall value of heat transfer coefficient. Now, when we are particularly talking of heat exchange between the cold fluid and hot fluid, so let us say I will draw, this is the length of a pipe where heat transfer is taken, and this is temperature. Now if both the fluids are flowing in the opposite direction, so for the hot fluid TH starting from here and going to the lower temperature TC. Now what is happening in the case of TH1, let us say TH2. Now cold fluid, it will be entering somewhere here. If it is entering here and it is going into this direction, this will be TC1 and TC2. So this is called counter current. So in the case of co-current flow, the hot fluid goes like this, TH1 to TH2, and the cold fluid goes like this, TC1 to TC2 along with length. Now what happens particularly here, along with the length of the pipe, there is significant variation in delta T. So we cannot simply take delta T at one point. So for that we need to take this log mean temperature difference, or we say delta T LMTD, log mean temperature difference, and this is defined as delta T. So this difference will be called, let us say delta T2, and this difference is called delta T1. So that now log mean temperature difference will be delta T2 minus delta T1 divided by ln delta T2 upon delta T1. It can be written either way, delta T1 minus delta T2 divided by ln delta T1 upon delta T2. So in this way we have to see this hot fluid entry and cold fluid out. It can be in either co-current or counter current mode. Now we will see one example here to how to calculate this log mean temperature difference. Fermentation media is cooled from 121 to 53 degrees centigrade in a double pipe heat exchanger. If cold fluid is flowing in the counter current direction and is heated from 4 degree to 75 degrees. So it says cold fluid is TC1 is 4 to 75 degree C, and hot fluid is cooled from 121 to 53. 121 to, it will be like this, 121 to 53. So this is 53 degree centigrade, this is 121 degree centigrade. Now we can calculate delta T1. Delta T1 will be 121 minus 75, 46 degree centigrade. So typically this T should be taken in degree Kelvin, but the difference will remain same, and this difference will be delta T2 53 minus 4 49. Now we can calculate delta LMTD, log mean temperature difference, delta T2 minus delta T1, 49 minus 46 divided by 49 minus 46 divided by ln 49 upon 46, and you will get the value in between these two values. What was the value here? It was 46, this was 49, and you got the log mean temperature difference value in between, that is 47.6 degrees centigrade. So going further, as we have discussed that this film thickness, particularly near the solid surface, it affects the heat transfer coefficient. So area available for heat transfer, this is an important consideration for design of heat transfer equipment, and surface area, it depends on what is the configuration, what is the size of equipment, and ultimately its cost. So, one important factor is to increase the heat transfer coefficient, because Q is directly proportional to U, it is directly proportional to A and delta T. And what are the factors which affect the overall heat transfer coefficient? Individual heat transfer coefficient, property of separating wall, and fouling factor. We have already discussed this. And the heat transfer coefficient, as I told, as it is regulated by the film, liquid film, it is directly proportional to the turbulence and inversely proportional to the viscosity of the fluid. So, based on this, there is a general form of correlation for heat transfer coefficient with the fluid properties. So, before going ahead, it says Nu is the Nusselt number, which is defined as it characterizes the convective heat transfer relative to conduction, or you say Nu is H is the heat transfer coefficient, D is the diameter, and K is the thermal conductivity. This is a function of Reynolds number, Prandtl number, and Grashof number. In addition, the viscosity in the bulk and viscosity at the wall. Mu B is the viscosity in the bulk solution, and mu W is the viscosity near the solid wall. So, Nusselt number, Reynolds number, we have already discussed. It is the ratio of inertial force to viscous force, defined as rho Vd upon mu, and if it is impeller Reynolds number, then U is replaced by Ni di and D is replaced by di. So, it becomes Ni di square rho upon mu. Prandtl number, it compares the momentum diffusivity with the thermal conductivity. What is the momentum diffusivity? Cp, thermal heat capacity, Cp into mu B, viscosity divided by the thermal conductivity. So, it is comparing momentum diffusivity with thermal conductivity, and it is independent of flow of a Newtonian fluid. Next number is the Grashof number, which is the ratio of buoyancy to viscous force. So, denominator is the viscosity, that is viscous force, and numerator is the particularly this density, that is related with buoyancy force. So, in fact, this Grashof number we have already discussed in the last lecture as well, and this is important here in natural convection, because there only this gravitational force will be important. Now, there can be a different scenario if you consider the heat transfer, particularly the heat flow to and from fluid inside the tube, and there is no phase change. Other option will be heat flow to and from the fluid outside the tube and still no phase change, and heat flow from the condensing fluid and heat flow to the boiling fluid. Now, we will be seeing different cases, that how heat transfer correlation vary for different scenario. The first is flow in the tube without phase change. In that case, Dittus Boelter correlation, it says Nusselt number Nu is H d upon K is proportional to 0.023, Reynolds number to the power 0.8 and Prandtl number to the power 0.4. So, if Reynolds number and Prandtl number is known, what is Reynolds number? Rho V d upon mu. What is Prandtl number? Cp mu upon K, thermal conductivity. So, if it is known, we can calculate what is the value of heat transfer coefficient. And this correlation is applicable particularly for turbulent flow, when Reynolds number is higher than 2100 and fluid viscosity is less than 2 millipascal seconds. And here the property of Nusselt, Reynolds and Prandtl number are determined at mean bulk temperature, means outside temperature, inside temperature divided by 2. So, here you can directly take mean temperature, and when we are seeing D, this is internal tube diameter, DI rather, and when we are dealing with the viscous fluid, the same correlation will be there. There will be slight change. It says 0.027 RE to the power 0.8. Prandtl number, the coefficient is now it is 0.33. In addition, one term is coming mu B, the viscosity, the bulk fluid divided by the viscosity at the wall to the power 0.14. Now we will be seeing next case, the flow across a single tube without phase change. So you can see the heat transfer coefficient for flow across a cylindrical tube. In that case, Nusselt number is proportional to a constant C RE to the power n and Prandtl number to the power 0.33, and the value of C and n are dependent of Reynolds number. For example, if you just see for the Reynolds number different range, what is the value of C and what is the value of n. In fact, if you consider a turbulent flow region here, the value of C will be 0.026 and the value of n will be 0.8. So, this is very much similar to this correlation 0.02 RE to the power 8. So, this table is available. So, depending on the, first you have to calculate the Reynolds number, then you have to choose the value of C and n in this correlation. Next is flow at right angle to a bank of tube without phase change. The fluid flows around the outside of the tube, and heat transfer coefficient for the cell side fluid depends on the geometrical arrangements of tube and baffle, and particularly this level of turbulence for the tube in line is less than that of staggered tube. Now there can be two different arrangement of the tube. So here you can see tubes in line, they are all in one line, and this is tubes in a staggered way. So it says level of turbulence for tube in line is less than that of staggered tubes, and what we are considering is heat transfer for the fluid flowing at a right angle. The correlation slightly changes here. It says Nu is now proportional to F is the constant, and here we calculate maximum value of Reynolds number to the power m and Prandtl number to the power 0.34. And in this way we calculate the Re max is calculated is D into U upon rho. D equals to the outside tube diameter, here U equals to the maximum fluid velocity on minimum free area available for fluid flow, and rho. So now D we are considering outside diameter. This is the maximum fluid velocity density divided by the viscosity, and these are the value if there is a inline arrangement or this staggered tubes. So in this way we calculate, these are the value depending on the value of Reynolds number, F and M value. So these tables are readily available and that can be referred for the given tube array configuration and Reynolds number, Re max value. Next comes if you are having the stirred liquid, and in the case of stirred liquid we are going to consider two different conformation. One is you are having the jacketed vessel and other is you are having the stirred tank. The heat transfer coefficient in the stirred tank depends on the degree of agitation as well as on the property of fluid. So in this correlation, if you just see heat transfer to or from a helical coil in a vessel. So, here we are calculating the REI means impeller Reynolds number, Prudential number, and this the same terminology is there. Mu b upon mu b is viscosity in the bulk, viscosity at the wall to the power 0.14, and this is applicable to all type of impeller system. And for the low viscosity fluids like water, we may consider viscosity at wall equals to the bulk viscosity. And for the viscous fermented broth, this viscosity at wall is greater than viscosity in the bulk. And now if you are having this jacketed vessel, so the correlation is slightly different. So, here this 0.9 is replaced by 0.36 and RE to the power 0.67 in place of 0.62, and that is it. There is slight change here, but at the end this Nu is proportional to Re to the power, let us say alpha, and PR to the power beta. So, we will quickly see one example here. A single pass cell and tube heat exchanger is used to heat a dilute salt solution for large scale protein chromatography. Salt solution passes through 42 parallel tubes. How many tubes? 42 tubes inside the heat exchanger at a total volumetric rate of, so the flow rate is F is given as 25.5 meter cube per hour, and the internal diameter is DI is 1.5 centimeter, and tube length is 4 meter, and viscosity of the salt solution mu b is 10 to the power minus 3 kg per meter into second, and density rho is 1010 kg per meter cube, and average heat capacity Cp value, heat capacity is 4 kilojoule per kg degree centigrade, and thermal conductivity K is 0.64 watt per meter degree centigrade. Now, we have to calculate the tube side heat transfer coefficient. So, how we will proceed further? As here we have to use different correlation. The first thing we need to calculate the Reynolds number Re. Re will be rho u d upon mu. Density is given, diameter is given, viscosity is given, u is not there. So, first you have to find the value of velocity. How we will find the value of velocity? Velocity we will find as the flow rate upon area. So, flow rate is given, we need to find the area. What is the value of flow rate? Flow rate is 25.5. What will be the area? For one tube the area will be pi r square. How many tubes are there? 42 tubes into 42. In this way we will find the velocity as 0.95 meter per second. And once the velocity is there, we can quickly now find the Reynolds number. Rho, what is the value of diameter? Diameter is 1.5 into 10 to the power minus 2 meter. Velocity we have just calculated 0.95, and density is 1010, and viscosity is 10 to the power minus 3. So, we will get the Reynolds value as 1.44 into 10 to the power 4. So, it says it is a turbulent flow. So, once it is turbulent flow, then we can use the given correlation. The correlation will be Nu as 0.023 into Re to the power 0.8 into PR to the power 0.4. Now we can quickly calculate the Prandtler's number. So PR will be Cp mu upon K. All the parameters are given. Cp is 4 kilojoule per kg degree centigrade. Mu is 10 to the power minus 3 and K is 0.64. We will get the value of PR as 6.25. Now from here then we can find out the value of Nu, that will be 0.023 into Re is 1.44 into 10 to the power 4 to the power 0.8 into 6.25 to the power 0.4, and we will get this value as 101.6, and this Nusselt number will be equals to H D upon K. Now we can find the value of H as Nu into K upon D. So Nu is 101.6, K is 0.64 thermal conductivity, and D is 1.5 into 10 to the power minus 2. We will get the value of H as 4335 watt per meter square degree centigrade, or you can say 4.3 kilowatt per meter square degree centigrade. So with this I will stop here. So today we discuss the first lecture of the heat transfer, basically the mechanism of heat transfer. Mostly in bioprocess the relevant is conduction and convection. So we discuss in detail, and further we discuss how to estimate the heat transfer coefficient using different correlations. Thank you.